Okay, now that we studied this thing about the curl of the electric field and Maxwell's law, so let's say that these things correspond to the so-called phenomenon of electromagnetic induction. So we say that when we have a time-varying magnetic field, we have an induction of electric field, and if we have a loop of a closed loop of wire, then we have as a result of this circulating magnetic electric field, we have a current we call the induced current. So an alternate magnetic field can induce a current in a closed loop, even if there are no generators in this closed loop. It's just a result of the electromagnetism. So this, which is what is written here, plus this mathematical thing which is called the Stokes theorem, this result allow us to do a simple calculation in a condition where everything is beauty, like the magnetic field is homogeneous, all the lines are perpendicular to the surface is a perfect circle. So in a simplified condition, let's say, we can calculate this thing, this integral, because if the path is circular, then this integral is just 2 pi multiplies the radius. R is the radius now, it's not the resistance of anything. And so this corresponds to the length of this circular path, and E is constant in this case. So if we know this, then by taking this into account, we can understand that this is the flux of minus the time variation of the magnetic field. We are just substituting this integral with this and the integrand with this. Then this magnetic field can be integrated in the surface of this circular path, which is just pi r squared, and we have the time derivative here. So then we consider the Ohm's law, that we said that an electric field in a piece of wire will produce a current density actually. Then if we integrate that current density in the area, which is the cross section of the wire, so we not to confuse this area with the area of integration of the curl of the electric field, we can write this, and therefore by substituting, plugging everything inside those kind of things, we can give an expression of the current. So basically we have to put J inside this equation and E inside this thing, and we get E from this equation that is relating E with the magnetic field, and then the result is this thing here. So we read it like this. We have a closed loop path, a closed loop wire, a magnetic field passing through this closed loop path. The radius of this closed loop path is r, and so therefore we see that for a given variation, time variation of magnetic field, the bigger the radius of this closed loop path, the bigger the current. So this is the first thing we have to notice. And then the second thing is that the faster the variation of the magnetic field, the bigger the current. So we are discussing this situation here, for instance, where we have a piece of equipment that can be a neural amplifier sending a signal to a to a computer that acquires the data. So maybe here we have an ADC, and here we have our op amp, and there is some distance between them. There are two wires because one is the signal and one is the ground. We cannot send a voltage, we only send a difference of voltage. And maybe those two pieces of equipment have a ground that goes here, another one goes here. We need to connect the ground together, otherwise we cannot send this signal. But it is possible that within the power, the mains of the let's say the power grid to which those two pieces of equipment are connected, there is also an unwanted connection connecting one with the other one. And so we have a big loop of wire, a little bit hidden, let's say, that is intrinsic in this connection of two pieces of equipment. So if we don't consider this kind of loops, which are called the ground loops, and if we don't consider the fact that there is an electromagnetism phenomena described by the Maxwell's equation, then inside this loop we can have signals going into magnetic fields that can couple with this loop. So the biggest source of magnetic field, alternate magnetic field we have is the one that is coming from the power grid, that is 50 Hertz, because we have to remember that we always have 220 volts at 50 Hertz all over the buildings, because there are wires inside the walls, there are alternate current, so there is an alternate magnetic field, and this magnetic field alternate is permeating everything basically, and so therefore this can couple with these loops, and if those loops are big because the equipment are far each other, then the area can be very big, and if the area is very big, then we have current flowing in this thing, alternate current, due to the induction. And therefore, if we have a current I flowing in the ground loop, and the ground loop is made of a wire having a certain conductivity G, and then it means that there is a resistance in this wire, a little bit of it, according to this conductivity, and then it means one bad thing for us. We know that a current flowing in a resistor will make a voltage. So our ground, having a potential equal to 0 everywhere, it's not like this anymore. Even if this wire is a good conductor, but if it is big, I mean if it creates a big loop, then we might have this problem. So the ground here is not the same of the ground here, and it is floating randomly, let's say, according to the noise which is present in the environment. So this situation is bad for us. So nowadays the way we technically solve this problem of the ground loop is by not creating ground loops. In the past that was difficult, because if you wanted to send an electrical signal from one point to another one into two different equipment, then you automatically created this ground loop. Nowadays there are systems for which the recording systems can run on batteries, and so it doesn't take the power from the mains, but from an internal battery. And also I mean, more than this, it is possible to send a signal from one place to another one with fiber optics so you don't have this ground loop anymore, which will corrupt your signal. It will create an artifact. So as a rule of thumb, try to avoid ground loops. Then there is another thing, and it's the last topic I want to speak of. I try to make a long story short because otherwise we need a lot of things about the electromagnetism. So you see this funny picture, there is one guy here, don't try to repeat this at home. So he's the electronic geek, so he built his own Tesla coil, so a sort of very powerful transformer that can create a very big source of voltage, and then you see a sort of electric discharge, very very powerful. Probably there are millions of volts here, and he's safe inside a sort of metallic frame. So I will never do this because this guy probably didn't understood one important thing, but let's say it's quite enough for him, which is the concept of Faraday cage. So if you are in this situation, I can make a drawing here. No, actually I already did it. It was this one. So we were speaking about the divergence of the electric field. So we computed the flux of the electric field. So when you compute the flux of something, you have to multiply the value of the vector field you are interested by something which is, let's say, the surface through which this vector is passing. So in mathematics, when we speak about infinitesimal surfaces, it means that there is a vector attached to it. We call it ds, and the direction of this vector is indicating the orientation of the surface. It's something like this. So like this. So this direction can be according to the direction of the field, or also with an angle, or with an opposite angle. So one pointing like this, the other one pointing like that. So this gives us the meaning of entering and exiting flux, entering in a surface or exiting from the surface. So the electric field is done in a way that if you take a closed surface, then the flux is zero if you don't have charges inside that surface. And this thing basically is what is called a Faraday cage. So a Faraday cage is a device, a very simple device, where you have a closed structure made in metal. So it's, we say, equipotential, so it has the same level of voltage all over the surface. And if you have an external field, this field cannot generate a net flux inside in the inner region. And so if there is no net flux, there cannot be let's say an active force on whatever charges can be inside. So it also works a little bit when we have time varying fields. So we cannot induce a field like a current if we are inside such kind of object, which is called the Faraday cage. And therefore this thing is a sort of shield from the point of view of the external noise. So this is a popular solution So if you have a sensitive equipment and at a certain point you want to try to reduce the noise, you can take all of it, you close it in such kind of Faraday cage that completely surround it. You put this to ground, and it's even not necessary to put it to ground because no flux can enter. So it would have any voltage, but a certain defined value. So this guy did this, but with a sort of approximation. He built around himself a Faraday cage, but with some apertures, because instead of using a full piece of metal, he used a mesh. So this can be a little bit dangerous or misleading, but we have to consider one thing, that electromagnetic waves traveling, they have a so-called wavelength according to their frequency of oscillation and the speed of light, which is what is written here. So c is the speed of light, f is the frequency of the electromagnetic disturbance we are considering, and lambda is the wavelength. N is the index of refraction. For say for vacuum or for air, this n is 1, so don't consider it for the moment. Lambda is speed of light divided the frequency of the oscillation. So it is possible to demonstrate that if we consider regions of space having a size which is smaller than lambda, then the electromagnetic wave cannot pass easily through it. So just to give you an idea, the speed of light is something like 3 by 10 to the 8 meters per second. So if you have an oscillation of 3 multiplied 10 to the 8 hertz, which is 1 over second, then you have a corresponding wavelength of 1 meter. So 3 multiplied 10 to the 8 hertz means 300 megahertz. So at 3 gigahertz the wavelength is something like a tenth of a meter, so it's 10 centimeters. It means that from the point of view of an electromagnetic disturbance, a radio signal having 3 gigahertz of frequency, let's say it's not very able to pass through an aperture that is smaller than 10 centimeters. And so all the frequencies that are below that thing will not pass through such kind of mesh. So from the point of view of the radiated electromagnetic waves, the mesh is a sort of high pass filter. So for this reason you don't really need to have a completely enclosed Faraday cage in order to have a shielding of a low frequency range, low frequency which is let's say from the DC from 0 till something like 3 gigahertz, because those fields cannot go in the cage. And just to give you an idea, 3 gigahertz is the range of the Wi-Fi or mobile phone signals. So I think the maximum frequency we have in the standard spectrum for telecommunication is around 5 gigahertz, maybe with the 4G or the new 5G standards. So if you have a Faraday cage made with a mesh having a size of a few millimeters, for all the signals that we have in practical real life, this is a good shield. The last thing I want to say, and then I'm done, is that we have to be careful about the apertures, because you might have sometimes Faraday cages with doors, because you need to open in order to put the thing you want to protecting, and then you close the door. But when you close the door can close like this, and if it doesn't close perfectly, but there is a little gap like between the two sides of the doors, then even if this gap is narrow, but it can be very long. And because the electric field has a direction, we call it a polarization. So some electric some electric field can enter if they have a direction matching the direction of let's say this slit that is formed by not closing completely a gap like the doors of a Faraday cage. If you do this, then you have a very bad situation, because the signal goes into, it's a radio signal, so it's alternating, and then it reflects all over the Faraday cage, and if you are unlucky, you can even get an amplification of that signal, because you can create, without wanting it, a so-called resonator, so like a bell, let's say, that will amplify your signal. So for these reasons, we have to take care about Faraday cages. So they might be implemented with meshes, but then we have to close them, because if we leave a side open, then it can also be that having a semi-closed Faraday cage is worse than not having it at all, because of this resonance. So this is another, let's say, trap that neurophysiologists can fall in. We have to take care about all those things, otherwise we can create extra noise that by trying to getting rid of it. Okay, so thanks for your attention, and that's it.
Thank you.